So here we have our Tetris clone, complete with appropriately Russian background and done in less than 400 significant lines of Python. The Tetraminos, as the Tetris shapes are called, fall at a constant rate, and the player can use the direction keys to rotate the falling Tetramino or move it right, left, or down. When the falling Tetramino can't move further down, any full line gets cleared and the next Tetramino spawns. The player can pause the game with the spacebar, and when the falling Tetramino can't move down but is still in the starting zone, the reddish area at the top, the game ends. Notice we don't have any sound, as we'll introduce sound in a later project. The bulk of the code is organized into classes. Only two of these classes, though, Tetramino and Tetraminotype, have multiple instances. The rest are treated as what are called singletons in object-oriented terminology. A singleton is a class which is only meant to be instantiated once. In truth, a singleton class acts more like a module of code than as a proper data type. You'll see singletons used frequently in a language like Java, where the language forces everything to go inside classes. Effectively, singletons in Java are an end run around the object-oriented design structure which Java imposes. In Python, singletons are stylistically useful as what you can think of as submodules. Rather than create a .py file for each of these pieces, we put them all in one file, each as their own class. In this program, the board class represents the play area, a coordinate grid where the Tetraminos go. And whereas each Tetramino on the board is represented by an instance of the Tetramino class, each Tetramino object has a property for its Tetramino type, which is one of the 7 instances representing the 7 shapes of Tetramino. So while the number of Tetramino instances changes as the game progresses, and while each Tetramino instance has a property referencing a Tetramino type, there are always 7 and only 7 Tetramino type instances throughout the game. Info display displays the text messages, including the number of lines cleared and the paused and game over messages. Input translates the user input events into the game commands, that is, moving the falling Tetramino and pausing the game. Be clear, though, that the actual pausing and moving are done by the game object and board object respectively. The input object is there simply to translate the input events. Given our very simple user input scheme, the input class is perhaps an unnecessary layer of abstraction, but it will be a useful pattern to expand upon in our future projects when the user input might get more complicated. GameTick is a simple timer used by our game class to determine when to move the falling Tetramino down and clear lines. And lastly, the game class does the high-level game logic, effectively tying together the board, info display, and input objects. So these are our classes. None of the classes inherit from any other, but their composition relationships still form a dependency hierarchy. The game instance contains the board, input, info display, and GameTick instances, and the board instance maintains a list of the Tetraminos on the board, all of which in turn reference a Tetraminotype instance. Just be clear that the composition relationships of a program don't always form a neat hierarchy, they just happen to in this program. So all of these classes are in the module GameTypes.py, but the resource loading, event handling, game loop setup, and most of the object instantiation is done in our main module Tetris.py, which is the module we run to run the game. The Tetris.py module starts out importing Piglet and our GameTypes module, then sets a few constants. Width and height are the dimensions of our window, board X and board Y are the display coordinates of the lower left corner of where the board is drawn, grid width and grid height specify the block width and height of our board. 10 by 20 seems to be the norm in most Tetris games I've seen. Block size sets the size and display coordinates of each block of the board. We then create a Piglet window with width and height, being sure to set vsync to false. We then load the resources of our game, in this case just 2 image files, the background image on top of which everything else is drawn, and an image containing the different colored blocks for the different Tetraminotypes. The resource.image function returns a Piglet image object. As we'll see, we can draw these images anywhere into the window with their blit method. The term blit is an old term derived from bit block transfer. In graphics, blit means to copy image data from one image to a frame buffer or another image, either in whole or in part. For reasons we'll discuss in a later video, using blit is the least efficient way to draw in Piglet, but it's simple and suitable enough for our simple game of Tetris. Anyway, once we have our two image objects, we then invoke the Tetraminotype class's static method called ClassInit. A static method, recall from my video on object-oriented programming, is a method which is really not a method but rather just a function that happens to live in the namespace of a class. That's why we can invoke ClassInit here via the Tetraminotype class object itself rather than any instance of Tetraminotype. In fact, at this moment there aren't any Tetraminotypes in the program. The purpose of ClassInit is to, as the name implies, initialize the class, that is, set up some properties of the class object. The purpose will be more clear when we look at the actual code. In any case, now that our resources are loaded and any classes that need initialization have been initialized, we then set up our initial game state. This means creating the object hierarchy we just looked at. Our top-level game object requires an instance of board, info display, and input. So we create those instances first and then pass them to the game constructor. The purpose of the other constructor arguments here we'll discuss when we look at the classes. Looking at the second half of Tetris.py, we register two event handlers on our window, onKeyPress and onTextMotion. The onKeyPress event triggers when we push down any keyboard key. The onTextMotion event triggers when we push down a direction key, up, down, left, or right. But it also triggers repeatedly as long as the user holds down the key. This repeated triggering, though, starts only after a short delay, the precise delay length of which is a system-defined keyboard setting. In both of these handlers, we pass the input to a method of our input object, which is responsible for interpreting the events. We also, of course, register an onDraw handler, which simply invokes the draw method of the game. Now, if our game didn't redraw the whole window every frame, we would want to invoke window.clear to draw on a blank slate. In this case, though, the first thing game.draw does every frame is redraw the background over the whole window, so we don't need to clear first. Clearing the window would just be extra work that doesn't accomplish anything. With our handlers in place, we also need an update function to update the state of our game on a regular basis. So the update function here is scheduled to run every 1/60th of a second. The real work, though, as you can see, is done in game.update. In other games, we'd pass dt, the delta time, the actual time passed since last invocation of the update function. We'd pass dt to game.update so that our game logic could account for variances in the invocation rate. In our Tetris game, though, the variances don't make a substantial impact on the gameplay, so we'll just ignore dt. And now finally, with our resources, game state, event handlers, and update function in place, we start the event loop with app.run, and our game begins. So that's all of Tetris.py. Looking now at GameTypes.py, we again start by importing Piglet. We also import random, a standard Python module, which in this case we'll use to select a random item from a list. So, looking first at the Tetraminotype class, its constructor takes two parameters, block image and local block coords by orientation, and these two parameters are simply assigned to instance properties of the same name. Block image is a Piglet image object, which is what we use to draw the Tetraminos. Each of the 7 Tetraminotypes will each have its own block color, so they have their own image. The local block coords by orientation argument should be a dictionary of 4 items, each with an orientation for the key and a list of 4 coordinates for the value. We'll represent an xy coordinate as a tuple with 2 integers. For example, the xy coordinate 3, 5 is represented as a tuple of 3 and 5. Recall that a tuple in Python is like a list but unmodifiable. Once you create a tuple, you can't change how many objects it lists or which objects it lists. Though the objects themselves referenced as objects of a tuple, those may still be modifiable. So in any case, the local block coords by orientation property contains the 4 block coordinates of the Tetraminotype in all 4 rotation orientations, up, down, left, and right. This will be clearer if we look at the creation of the 7 Tetraminotype instances, which is done in ClassInit. As mentioned, ClassInit is a static method, which is why we use the static method Decorator. Static method is a Python built-in function which wraps a function object as a static method object. A static method object behaves just like a function object, but with the difference that when defined at the top level of the class, as it is here, it is not treated as an instance method, meaning that there is no implicit argument for an instance object. That's why this method doesn't have a first parameter called self. So ClassInit becomes a static method attribute of the Tetraminotype class object itself, which is why we invoke it as tetraminotype.ClassInit. Anyway, what ClassInit does is create an image for each color of block. It does this using the block's image's getRegin method, which returns an image which is a portion of that image. A portion, in this case, of block's image. So the first line here assigns to green an image object which is the portion of block's image with its lower left corner at 0, 0, and which is block size by block size in dimensions, in width and height. The remaining calls all do the same thing, but starting at chords one block size further right. So we end up with image objects representing each block-sized portion of the block.ping file. As we'll see in later projects, Piglit actually provides more convenient methods for getting regularly spaced portions from an image. Here we're just accomplishing the same thing in a direct and obvious, if less convenient way. So once we have these images, each representing a different color of block, the rest of ClassInit assigns to the Tetraminotype class a property called types, which is a list of 7 Tetraminotype instances which we create here. For brevity here, we're just showing the first 2 instances. But as you can see, for each instance, for each type, we have 4 lists of coordinates, 1 for each rotation orientation. And these coordinates are expressed in local terms, not in terms of the whole board grid. When we place tetraminos on the board, we will translate from these local coordinates to board coordinates. So, for example, because a square looks the same when you rotate it 90 degrees, the square type has the same coordinates in all 4 rotations, 0, 0, 0, 1, 1, 0, and 1, 1. But those are the local coordinates. So if, say, a square tetramino is located, say, at board coordinates 5, 5, then we'll need to translate the local coordinates of its blocks to 5, 5, 5, 6, 6, 5, and 6, 6. This, though, is done elsewhere in code, which we'll get to later. Lastly here, the Tetraminotype class has another static method which simply returns one of the 7 types at random. This is done with the Python module random, which is a function choice that takes a list and returns a random element of that list. So when we pass the types list to choice, it returns one of the types at random. Looking now at the Tetramino class, the class itself has a few constants. In the top line, range 4 returns a list with the numbers 0, 1, 2, and 3. And in Python, as a convenience, we can assign the respective elements of a list to variables by listing them with commas. So here, right is assigned to 0, down 1, left 2, and up 3. These constants here are used as enumeration values of the 4 rotation orientations. It's arbitrary what value we assign to these variables as long as they are all different and stay unchanged for the life of the program. But we can then use these enumeration variables to refer to the 4 orientations, which is what we did when we created the Tetraminotype instances. The Clockwise rotations dictionary here defines the clockwise transition through the orientations. You go from right to down, down to left, left to up, and up to right. In the constructor, we give the Tetramino instances 5 properties. An x and y coordinate designating the tetramino's location on the board, a random tetraminotype, the starting orientation right, and a list of the coordinates on the board of the tetramino's blocks. The calc blockboard chords method, which creates these chords, is quite simple. First we get the local block chords for the type and orientation of this tetramino, which are in the local block chords by orientation dictionary of the type instance. We then translate from each local coordinate to a board coordinate by simply adding self.x to the x component and self.y to the y component. And remember that each xy coordinate is expressed as a tuple of 2 integers. So we create a new list grid coordinates, iterate over the local block coordinates, calculating each new grid chord by retrieving the local x as chord 0 and adding self.x, and retrieving the local y as chord y and adding self.y, and then appending each new coordinate to grid chords. Once we have our new list of translated grid chords, we can return it. The Tetramino class also contains methods for moving the tetramino on the board. We can set an arbitrary position, which we do when we first place a tetramino on the board, We can also move the Tetramino down, up, left, right, or rotate clockwise or counterclockwise. To move down, we simply decrement self.y. To move up, we simply increment self.y. To move left, we decrement self.x. And to move right, we increment self.x. To rotate clockwise, we use the Clockwise Rotations Dictionary, and to rotate counterclockwise, we use it 3 times, because rotating clockwise 3 times is the same as rotating counterclockwise once. Lastly, note that, very importantly, after all these modifications, the blackboard chords are recalculated. The Tetramino command method is a convenient interface for invoking all of these move methods. The command argument is one of 4 enumeration values from the input class: move down, move right, move left, and rotate clockwise. The undo command method does the inverse action of the command argument. For example, move down triggers a call to move up. When a row on the board becomes full, it's supposed to get cleared. This requires removing all blocks from the row and adjusting all blocks above that row down by 1. Because this is only done to settled tetraminos and never to a still moving tetramino, this can be done simply by directly modifying the blockboard chords properties. So the clear row and adjust down method of Tetramino does this for one Tetramino instance. We first create the list that will replace the current list of blockboard chords. Then we iterate through the current list for each chord with a y component greater than the row to clear. We adjust the y component down by 1 and add the adjusted coordinate to the new list. For each chord with a y component less than the row to clear, we add the coordinate as is. So notice that we excluded any coordinate with a y component equal to the row to clear. This effectively removes those blocks from the Tetramino. So we assign the new chords list to self.blockboard chords and return true if the Tetramino still contains any blocks, otherwise return false. Finally, the Tetramino draw method blits the Tetramino on screen. To do this, though, requires translating the grid coordinates of its blocks to screen coordinates, but this is left up to the board class. So here we expect to receive the screen chords as an argument. Then at each screen coordinate, we blit the block image of this Tetramino's type. The board class starts with a few constants. Starting zone height defines how many rows exist at the top of the board, above the field of play. Next x and next y define the grid location of where to display the next Tetramino, the Tetramino that will fall after the current falling Tetramino. By giving next x a negative value, the next Tetramino actually appears outside the board to the left, which is where we want it. Arguably, the next Tetramino isn't properly a part of the board because it's not actually on the board, but it was simplest to implement this way, even if it's a bit hackish. Anyway, then in the board constructor we have x and y parameters that define the lower left corner screen coordinates of the board. Grid width and grid height define the grid dimensions, and block size specifies the size of each block in screen coordinates. The spawn x and spawn y properties define the grid coordinate at which falling Tetraminos spawn. Note that there isn't any particularly good reason why x, y, grid width, grid height, and block size are all parameters, but spawn x and spawn y are not. In general, you parameterize those properties which you want to be configurable externally from the class. In this case, it just seemed to make sense to make these properties externally configurable, but the spawn coordinates not externally configurable. We also have properties for holding the currently falling Tetramino, the Tetramino that will fall after that, and all other Tetraminos in a list. The falling Tetramino and next Tetramino properties are configured by the spawn Tetramino method, and the Tetramino list starts out empty. Spawn Tetramino is not just called in the constructor, but also every time a new falling Tetramino is needed. The next Tetramino becomes the falling Tetramino, and a new Tetramino is created to replace the next Tetramino. Both Tetraminos are then positioned, the falling Tetramino in the starting zone, and the next Tetramino off to the left of the board. The command falling Tetramino method sends a move command to the falling Tetramino, but after the move, it tests whether the current position of the falling Tetramino is valid, and if not, it undoes the command. Invalid position here means that any block of the falling Tetramino is either out of the board bounds or overlaps another Tetramino. So we perform the valid position test by first collecting all coordinates of the blocks of the other Tetraminos. We do so by iterating through the list of Tetraminos and adding their coordinates to the non-falling block chords list with the extend method. The extend method of a list, recall, takes another list as argument and appends every item of the argument. Once we have this list of coordinates, we then iterate through the block coordinates of the falling Tetramino, testing whether the chord is out of bounds or whether it matches any chord in non-falling block chords. If either case is true, the position is invalid, and so the method returns false. If we get through all these tests without finding any out of bounds or overlapping coordinates, then the method returns true. If you're not familiar, the Python in operator returns true if its left operand equals any item in its right operand. So here the expression chord in non-falling block chords returns true when chord equals any item in non-falling block chords. The find full rows method returns a list of indices of the rows which are fully occupied by Tetramino blocks. So for example, if just the bottom two rows are full, this method returns a list of 0 and 1. It does so by first constructing a list of all Tetramino coordinates, just like in isValidPosition. We then tally up the blocks in each row in a dictionary row counts, whose keys are row indices and whose values are the tally for that row. So first we iterate through all row indices, assigning each row index key the value 0. Then we iterate through the block chords, incrementing the value of the appropriate row index for each. For example, when chord 1, the y component of the chord, is 5, we increment the tally in row counts for the key 5. Once we have our tallies, we create our list of full rows, adding every index from row counts with a tally equal to the grid width of the board. Recall that when we iterate through a dictionary, as we do here, the keys are in no discernible order. Consequently, our indices in full rows will be in no particular order. To clear a single row of the board, we have clear row, which invokes on each Tetramino the method clear row and adjust down. If the Tetramino still has remaining blocks, clear row and adjust down will return true, in which case we add it to the new list of Tetraminos. So effectively, Tetraminos without any remaining blocks get discarded. The clear rows, plural, method does the same as clear row, but to multiple rows. Because clearing a row moves every block above down by 1, we need to clear the rows from top to bottom. This simply requires sorting the row indices in descending order, which we do here with the list sort method with the reverse argument equal to true. The board class's updateTick method, as the name implies, updates the board for every tick, the moments where the falling Tetramino moves down whether the player directs it to or not. The complicated part is when the Tetramino can't move down any further. We detect this by moving the Tetramino down regardless and then testing whether the position is valid. If invalid, we undo the move, add the falling Tetramino to the Tetraminos list, find the full rows and clear them, test that the game is lost based on whether the falling Tetramino is still in the start zone, and assuming the game is not lost, then spawn in the next Tetramino. Finally, updateTick returns two values in a tuple, first the number of rows cleared, and second a boolean of whether the game is now lost. The isInStartZone test is done simply by testing whether any block chord has a y component greater or equal to the grid height. Lastly, in the board class, we have a method for converting grid coordinates to screen coordinates. Self.x and self.y, recall, are the screen coordinates of the lower left corner of the board. So we can get screen coordinates simply by adding these screen components to the grid components multiplied by the block size. For example, for grid coordinate x equals 5, we multiply 5 times the block size and then add that to self.x. Once we have screen coordinates for a Tetramino, we can draw it. So in the board draw method, before drawing each Tetramino, we first get its screen coordinates to pass to the Tetramino's draw method. We first draw everything in self.tetraminos, then the following Tetramino, then the next Tetramino. The info display class has a few constants, rows cleared x and rows cleared y, which are the coordinates at which to draw the number of rows cleared. In the constructor, we create 3 labels, one for the rows cleared, one for the game paused message, and one for the game over message. The paused and game over messages are centered using the window dimensions, which is why the constructor takes the window object as a parameter. Lastly, we have two flags, show paused label and show game over label, which determine whether the paused label and game over label get drawn. To show these labels, we set the flags to true, and to hide them, we set the flags to false. The setRowsCleared method simply updates the number of rows cleared that is displayed by the rows cleared message. The draw method, of course, draws the labels. In the case of the paused label and game over label, their respective flags must be true, or else they won't get drawn. The input class contains enumeration values representing the 5 user actions: toggle pause, move down, move left, move right, and rotate clockwise. In the constructor, we simply create one property, action, which holds the last user action. In a more complicated game, we would possibly want to retain a recent history of user inputs for more complicated behaviors, but in our simple Tetris game, we get away with just keeping track of the last user action. In the process key press method invoked when an on key press event occurs, if the key pressed was the spacebar, the action is set to toggle pause, otherwise nothing happens. In the process text motion method invoked when an on text motion event occurs, the left key sets the action to move left, the right key sets the action to move right, the up key sets the action to rotate clockwise, and the down key sets the action to move down. Lastly, the consume method returns the last action and also sets self.action to none, because we want each user action performed only once until there's more user input. The gameTick constructor sets two properties, tick and started, by default to false. The idea here is that we invoke the isTick method in each iteration of our game loop, but we only want it to tick, that is to return true, at regular intervals. In the first call to isTick, self.started by default will be false, so we take the first branch of the if-else ladder. Self.started gets set to true, the setTick function gets scheduled to run after next tick time elapses, and isTick returns false. Once next tick time elapses, setTick will run, setting self.tick to true, such that the next invocation of isTick will take the second branch, setting self.tick to false, scheduling setTick to run again after next tick time elapses once more, and isTick returns true. All the isTick invocations in between will return false. So as long as we keep invoking isTick with the same next tick time argument, it will keep ticking, that is, return true, at regular intervals. If we desired, though, we could change the next tick time on each tick, so we could have our Tetris game speed up as the player clears more and more lines. That's a feature I've omitted, but it would probably take only a few more lines of code in our game class. And looking finally at the game class, its constructor sets properties for the 4 parameters passed in: the board object, the info display object, the input object, and the background image. In addition, self.paused and self.lost are set to false, numRows cleared starts out at 0, tick speed is set to 0.6, as in 0.6 of a second, and ticker holds the gameTick object we'll use to trigger the board update ticks. If you're wondering why the gameTick instance is created in the constructor while the board, info display, and input instances get passed in as arguments, one reason is that 2 of those objects require their own constructor arguments, but the real reason is that it's generally better object-oriented practice to create top-level objects separately. In this particular case, it would be neat and convenient to just create these instances in the game constructor, but that kind of object bundling creates inflexibility that hurts us down the line when we try to evolve a codebase. Anyway, the addRowsCleared method updates the tally of cleared rows and adjusts the rows cleared message accordingly. The togglePause method toggles the self.paused property and sets the showPaused label flag accordingly. The gameUpdate method, which remember is scheduled to run every 60th of a second, updates the game state. If lost is true, the game is over, so we simply show the game over label. If the game is not lost, we get the last command from the input object, and if the command is togglePause, we invoke togglePause. Then, if the game is not paused, we first test if the command is not none and if the command is not equal to togglePause. If so, the command is an action concerning the following Tetramino, so we pass the command to board.command following Tetramino. Next, if the ticker's isTick method returns true, we invoke board.updateTick, which, recall, returns a 2-element tuple. First, the number of rows cleared, and a boolean indicating whether the game is now lost. Lastly, in update, we add the rows cleared. The very last piece of all is the gameDraw method, which, recall, is the only thing invoked by the onDraw event. This draw method first blits the background image over the whole window, then draws the board, and last draws the info display. Be clear that the draw order of overlapping elements matters, so we must draw the background image first, or else it will draw on top of the board and info display, in which case we'd never see the board or the text messages.